Cool. Now we're ready to get started. All right, so got a bunch of data here, a bunch of information, got a formula. Where would we start with this? We're just trying to come up with a reasonable structure. And there's any number of places we can start, but what's usually the simplest place?
Yeah, looking at the
Let's look at the IR. What can we rule out? We know
alcohols.
no alcohols, which also means carboxylic acids, right? So we've got 4 oxygens, however, no OHs. Okay, so
Ketones, that's
So-
usually the
carbonyls would make sense, yeah, in that 17 range. If not ketones, then at the very least carbonyls. Does it seem like it's gonna be aromatic?
No. C8. Oh, or, no.
There's enough carbons for it to be a ring structure, but there's too many hydrogens, right?
Right, yeah.
So
No.
we know it's not aromatic, and we can also figure that out from the proton NMR as well. There's nothing down here in that 6.5, 7.5 range. Alright, so what else can we figure out about this, just in general terms?
Only sp3 carbons.
It definitely looks like, I would actually probably get out a ruler, but yeah, looks more like it's gonna be all sp3 carbons. No sp2 carbons. Remember the sp2 carbons? That bond is a little bit stiffer, so it's higher energy, so it shows up above 3,000. Then maybe one of these could be an aldehyde, but probably not.
Or I guess no sp2ch bonds, because
There's no sp2ch bonds, yes. There might be some sp2 carbons, because of the carbonyls. The other thing we can tell about this, look how few signals there are in the proton NMR. So we've got 14 hydrogens, but only 3 signals. What does that tell us? Symmetry. This is going to have a large degree of symmetry. We do have a methyl group with 2 nearby hydrogens. And we have a singlet. So something with no nearby hydrogens. And then we've got a quartet. That's not as useful immediately. We'll use that to rule stuff out later, right? Anybody remember how the carbon NMR works here? Let me adjust the figure, see if we can get more on this, where we can see it. A little bit more. Does anybody remember what the DEPT 135?
My notes remember.
Your notes remember somewhere?
Yeah. So if it is turned downward on that, that means it's 2 hydrogens, CH2.
Yeah. Or no hydrogens. It's an even number of hydrogens, I believe, right?
It had just like a flat line for no hydrogens.
Okay, so no hydrogens won't show up.
Yeah.
Down means even number of hydrogens, so CH2.
And up is 1 or 3.
In one or 3. Which makes sense because we know we've got a methyl group based on where the protons showed up. And here's our proton decoupled, meaning just our straight carbon NMR. So there's only 4, despite the fact we've got 8 carbons, there's only 4 unique carbon signals. And one of the carbon signals doesn't show up in the DEPT 135. So this one is our Probably our carbonyl carbon, this is so far de-shielded. And that makes sense, so it should be a totally symmetric molecule. In some respect, right? 4 carbon signals, 8 carbons total. What could we be working with? We know we've got this as a fragment,
2 of those probably.
probably 2. And that's where the integration might show up. None of these look like their integration is way more than the others. If we did get out we did get out a ruler, we'd probably see that this looks like it's about 1 to 2 to 3. Which would make sense because we know this is a methyl, right? So our quartet, that's our CH2, which means the carbon that's next to it here probably doesn't have any hydrogens on it. Otherwise, this quartet would be a quintet or a sextet. So,
And then based on where the proton decoupled, that most de-shielded one, yeah, my guess is gonna be an ester.
esters would make sense. It's some sort of symmetrical ester.
Yeah.
In fact, it might even make sense to put it and then double it. Because then we get that high degree of symmetry.
And you're left with oxygen.
Ace, our problem with this one. So we have 3 signals here, this would only give us 2 signals. Oh. There's only
Oh, we need more carbon.
more carbons.
Yeah. Could there be 2 just CH2s in the middle between the 2 ester carbons? It's like a chain of 2 CH2s.
That would show up as a triplet.
That's true.
Yeah, it has to be something with no. Except we're looking at that singlet.
So this is our SP2. So we're looking right here. So no nearest neighbors. And that would give us a total of 10. So we do need 4 more hydrogens. So this does have the right degree of unsaturation.
Yeah.
So we're not looking at a ring structure. What else could we could. Methyl group is what throws it off a little bit because we know we've got the CH2. And we can be pretty certain that we're gonna have an ester. Times 2.
Yeah. 1, 4 times 2 carbon.
With no nearest neighbors.
And we know it has to also be H2, has to be a CH2, just with how many hydrogens we have left over.
Right, so actually, I know I said 1 to 2 to 3, but maybe this might be 1 to 1 to 1.5.
Yeah.
Or
So 2 to
maybe
3.
2 to 2 to 3.
Yeah. And then, yeah, 'cause it'll be a CH2,
right?
For sure. So we know it'll be a CH2.
We know it's gotta be a CH2.
And there's one that's significantly more de-shielded than the other.
So,
And then, what if it's not an ester? What if it's like there's like an ether going to a CH2 going to a ketone? That word,
so
like, yeah. Or no, because then carbons are down. Yeah, because then we don't get that.
That would still give us a clean singlet for these
No, for
hydrogens.
those, yeah, it would. Oh, it would, yeah.
All right, we're gonna let this one marinate. These are all the things that we wanted to talk about. I actually don't remember the answer to this one. So I'll look this one up. When we go to break here. But this is also a good approach to these in general, right? Get some stuff on paper, get some ideas, remind yourself the relevant concepts. Then we'll come back to it. After it's got a chance, your brain has a chance to digest it a little bit. So we'll come back and talk about it more after break. All right. So let's just let's do some reactions. We talked about aromatic compounds. Let's talk about oxidation of aromatics. So there was one way we had of taking phenol and oxidizing it. If you remember back from the alcohols chapter. What happens when you put dichromate with phenol? Who's done your review assignment? So with phenol, we got something that it starts aromatic. We actually lose the aromaticity when we expose it to dichromate. Similar, big benzoquinone. So which is kind of like a benzylic ketone.
Yeah. 1 second.
We get that. But other than having a phenol being oxidized, dichromate's a pretty strong oxidizing agent. We just put dichromate with benzene though, nothing happens. And it turns out that the dichromate, even as good of an oxidizing agent as it is, you still need sort of a handle. You need something to start the reaction for anything to happen. So if we just put an alkane with dichromate, we get nothing happen. But if we put a benzylic alkane with dichromate, it basically chops off the end of it. So regardless of how big this section is, this is a little bit of a blunt instrument because it's not going to be subtle about how it does this. If you have a benzylic carbon, it turns it into benzoic acid or a benzoic acid if it's got another substitution. So anytime you've got a carbon adjacent to a benzene ring, you're going to see this happen.
It's tertiary. It's really.
It's the resonance of the benzene ring.
Through the tertiary.
Right. So and even we want to be careful with the term tertiary because these benzylic or these phenyl carbons are really its own thing. Aromatic carbons, we don't really classify them as either secondary or tertiary. They're kind of always just aromatic carbons. But yes, if we're just strictly counting carbons, then technically, yeah, that's a tertiary carbon. But it's not the tertiary carbon that the aromatic carbon that gets oxidized, though. It's the one adjacent to that. And so I'll remind you of that terminology. Benzylic means not part of the phenyl group, but adjacent to it. So just like allylic was not, these two were vinylic, and this was allylic. Might be another L in there, I don't remember. These are aromatic or phenyl. that carbon is benzylic.
Does the benzylic carbon here need to be Sp3 for this reaction to happen?
It needs to have a hydrogen.
Okay.
So that's the next qualification. I'll get some markers that work a little bit better too. Can we go to break here? Is it needs a hydrogen, so we see this, it happens most reliably with alkanes, you're not really gonna see it, this reaction used. When you've got another sp2. Here, it's typically used on sp3 carbons. Right, but specifically works the best or only works when you have a hydrogen on that benzylic carbon. And when you try to do this reaction with a quaternary carbon in the benzylic position, nothing happens. So as much of a blunt instrument as it is, it does still have its limitations. And the rest of those carbons, when we chop these other carbons off, are probably just going to be oxidized to be some other. Some of them will probably be oxidized all the way to CO2. Some of them are going to be oxidized to an alcohol or some other molecule, but basically it's not predictable.
So it doesn't really matter how long the
Correct.
cane is, it will just always go to benzylic acid, like acid.
Yeah. And we basically ignore the fact that that's not balanced. Like we've been doing in organic chemistry, right?
Don't pay attention to it, don't even think.
Yeah, those are there for now, but they won't be for long.
Something floats away.
Yeah. This is the sort of reaction that gives organic chemists a bad name when we talk to biologists. Well, it's a good question, and it really does illustrate the difference between biochem and organic chemistry, because in biochem, everything is so narrow. Because all of these enzyme catalyzed reactions are so specific. Everything has to be just so, because you can only have these reactions happen if everything fits into the active sites properly. And even if there's more than one active site per enzyme, everything has to be present. And so biochemists get to be really, really picky about that. Organic chemists, we see this like, well, I don't know, some other carbon stuff's around too. Right. All right, so let's practice with these. Oops, sorry. Every time I do that.
Do you have these slides on?
They're not posted yet. I'll get them saved and posted when we go to break. Getting a list of things to do during break.
It's all just IR spectrum stuff.
Yeah, no, I'll find it. Slides, markers. I'll do markers right now while you're working on this.
There's some markers out on the table.
Yeah, I try not to grab those ones, 'cause I like to leave them out. I have a big bunch of box in my office.
I think it's it's no more than me that is.
Well, usually every week we'll just go there and see with you.
Yeah.
Just random.
Well,
Well, yeah, I mean, they have something in the library, but I like to have my own little staff.
there you go.
Because most of them in the library, they fucking die out pretty quick. And I'd rather have my own that don't die out.
It's kind of like one that we're all together.
They're all fucking everything.
All right. One thing I saw. So, what's the common name of this first molecule? Do you remember? Methylbenzene is better known as,
Toluene.
that's the one, toluene. So toluene just turns straight into straight benzoic acid. Which one might have a common name? So toluene gets its own name, but that's just ethylbenzene. So methyl ethylbenzene or ethyl toluene. It's gonna turn into
1,3-dibenzoic acid.
yeah, so we're gonna get benzoic acid over here, one over here. When you a dibenzoic acid actually has a common name too. The only reason I remember this one's one of the ones where the spelling is obnoxious. Is phthalic acid. Like remember phenolphthalein? Exactly, so phthalic acid, in particular, this is M. Phthalic acid.
That's, yeah.
Oh,
And that's one, I probably should look up where that came from originally because. I'm sure it's interesting, it's likely Greek.
that word described.
Yeah,
Yeah, that.
yeah. Or phthalate, the deprotonated form is phthalate.
Just don't forget the TH when you pronounce it.
Yeah, yeah, exactly. All right, and then last but not least, yeah, those ones are gonna react, the TBO groups not.
Yeah.
And this is also subject to stoichiometry, having enough dichromate.
Right.
But at the same time, we don't really, this is one of those reactions that doesn't happen reliably halfway. So we kind of, you're gonna get a whole mess of products. If you try to only add one equivalent of dichromate, it's not gonna work, not predictably. So just, in this case, assume you have excess dichromate.
Should we write down excess? Might as well.
It's one of those, the dichromate is actually one of those molecules that actually, I'm not actually sure what the stoichiometric ratio is. Because it'll react with more than one equivalent.
Okay.
But I think that's probably why it's not written as excess, but assume excess. Like this one, it's pretty reliable. Like basically, as long as you've got enough dichromate, you're gonna get this as your major product. If you're chopping off some other carbons along the way, it's the other side that's not as reliable. Okay, so the other oxidation that has to happen to this extra, it's not gonna just make methanol. Because if methanol is exposed to more dichromate, methanol oxidizes further, you get all the way to formic acid, and then actually methanol might actually oxidize all the way to CO2. But if it's a longer chain, you might wind up making the carboxylic acid, but you're gonna have some other chunks sort of still floating around it, so we don't rely on it. They're easy enough, we don't even have a mechanism for this one, so.
Yeah. Yeah, that was just.
That's a piece of cake, right? Just a little appetizer. Some other reactions to review when it comes to benzylic carbons. So we're still not even touching the benzene ring yet. These are also benzylic reactions. We did have our benzylic carbons did have certain reactions that worked really cleanly. So, and this is really the shorthand. If other oxidizing agents will work, other than dichromate, sometimes you just see O in brackets, just means oxidation. So if you put it with an oxidizing agent, you get the benzylic acid. The most common one is dichromate, but if you remember, we're trying to phase out chromates as much as possible because they're really nasty. I did wind up watching most of that Toxic Town Netflix series about England. It is actually pretty good. Took place in the 90s and early 2000s. And they were cleaning up a steel mill. So basically the process of trying to reclaim the land from from all the toxic pollution from the steel mill, which is a lot of chromium. They use chromium in making steel. Wound up being released as dust. And they just coated cars when they were trying to reclaim the land to make the land more usable. They wound up just spreading chromium across the entire town. Yeah, so it's like we don't learn our lesson as humans. Anyway,
The radical bromination, that's with the NBS.
that's with the NBS, so it's similar to the allylic bromination. Which again, we use the NBS to keep the concentration of the radicals and the concentration of the bromine down. To avoid, we don't have to worry as much about brominating benzene rings because we're not going to do that. When we're trying to do the allylic bromination, we have to be careful not to have Br2 present because then we get that dibromination in as an addition reaction. We don't need to worry about that as much here because the benzene is so stable. So we probably could just use bromine with UV light. NBS is going to be your standard though. And then once we put a bromine on it, it's just like anything else. We can do SP or SN1, SN2. So we had a lot of, this was sort of our way to take something that doesn't have much of a handle, so to speak, and add functional groups to it that we can then do stuff with. And then it turns out we can take the acid, we can actually convert that to other functional groups as well. We can reduce it as well if we wanted to make a benzyl alcohol. If you remember what was our super strong reducing agent that would reduce even acids? It's not sodium borohydride, it was lithium aluminum hydride. Good. So once we get here, if we wanted to make this molecule, there's actually two ways that are drawn up here. We could oxidize it to the acid and then use lithium aluminum hydride to take it to the benzylic alcohol. Which, again, another common name just because the IUPAC name would be a mouthful. That molecule is benzylic alcohol. Because the IUPAC name would be a phenylmethanol, which is not that hard to wrap your head around, but it doesn't really capture how that this is the largest part of the molecule. So you will see both of those names from time to time.
So benzyl or
Benzylic.
I said benzylic, but now that I'm thinking about it, it might be benzyl. BENZYL. Either of those is going to give you the right molecule if you look it up. It's a benzylic carbon, but it might be benzyl. Now that you mention it. That clock is fixed. I just did the same thing. It's 10:36. And as we mentioned before, here's some more specific conditions. We can hydrogenate aromatics, specifically benzene. Similar conditions would probably work for most aromatics. Obviously, you're gonna have to change if we're doing this for naphthalene, we're gonna have to change our stoichiometry. But similar reactions would probably work for most aromatics, just benzene's the most well studied and most common, so.
platinum is a catalyst as well.
Likely. This is clearly what's considered well, it is the textbook definition. But yeah, platinum would probably work too. And 100 atmospheres and 150 Celsius is doable.
Yeah.
If you look at the scuba tanks, scuba tanks are rated, I think, up to 200 atmospheres. The inside of the tank. So we can build reaction vessels that can handle this. But obviously it's not gonna be as easy. We're not using lab glassware to do this.
No.
And there's also, if you do a very exothermic reaction in a sealed tube of metal. You know, there's the chemistry name for that, we call that a reactor. But there's also a common name for what can happen, it's called a pipe bomb.
Yeah.
Right, so obviously we're gonna wanna be careful trying to do that. Again, this is why chemical engineers are paid so well, is because they have to design it in a way that it doesn't blow up.
Yeah, the like fire department air tanks are rated at 300 atmospheres.
There you go, okay, and those are a little bit more hefty
Oh,
than
yeah.
scuba tanks,
They're heavy.
yeah. However, this also gives us the ability, the fact that the benzene doesn't really want to reduce. Or be hydrogenated, means that we can hydrogenate. Vinyl groups or alkene groups, even if they're conjugated with the benzene ring, as long as we're not breaking the benzene ring. We can do that under normal conditions. A little bit more atmospheric pressure than normal, just because there is that resonance. But that's a reaction we've seen before, right? Hydrogen, platinum, and this is at room temperature. Which is really handy, makes it really easy to selectively reduce. All right, however, there is one other way we can break the aromaticity without fully reducing it. And again, it's not a particularly easy reaction to do. It's very similar to the dissolving metal reaction. We need sodium metal in methanol and ammonia. Under these conditions, we break the aromatic ring. Well, the ring is still a ring, but we break the aromaticity aspect of it. We reduce 2 of the 6 carbons without reducing all of them.
Right. He's like, I want to put sodium, methanol, and ammonia.
Well, sodium is a fairly strong reducing agent because it's trying to give away its electrons, right? So they probably were just looking at this as, well, if I'm trying to reduce this, let's just try selectively stronger and stronger reducing agents. And even this one has some, the birch reduction in particular, specifically has a column 1 metal and ammonia, but there's actually other variations of it. In fact, if you Google birch reduction, less than halfway down the first page, you're gonna start getting hits for methamphetamine synthesis. Because if you use lithium instead of sodium, you can actually get that from batteries. And so if you take the lithium from batteries and put it in, reduce the lithium so it's a metallic state, and you can buy ammonia over the counter. You can use that but it's not breaking down. I think the lithium is not strong enough to break the aromatic ring. Because amphetamines have an aromatic ring that you want to stay as an aromatic ring. It reduces a benzylic carbon, I think, if I'm remembering properly. It's been a while since I brushed up on my methamphetamine production. But yeah, you cast iron that. I remember when I was first reading up on this one to make these slides, I kind of, why am I getting all these like science madness forums and like, all these DEA flagged websites? It's because, This is why we can't have nice things, right? So in this case, the weird aspect of it is that you get it, you completely break all conjugation, but you're still left with two alkene bonds. So there's no conjugation left because you have an sp3 at both points in the para position relative towards each other. Right, and this one, you'll be happy to know we do have the mechanism for. Let me move it up again so we can see it better. You know, we do like to be able to explain these named reactions. Part of the reason that they get named is because Birch might not have been the first person to do the reaction, but they're probably at least partially responsible for figuring out the mechanism. And you do see there are some similarities in the dissolving metal reaction. And the interesting thing here, the thing that makes this a really tricky mechanism, is it is a free radical mechanism. Right, because sodium only has one electron to give. If it's going to give it to the benzene ring, it has to do it one electron at a time. Which usually also means you need a 2-to-1 ratio. You have to do it twice. Because we got to make these even number of electrons at some point. Alright, so you donate an electron to one of the benzylic carbons, doesn't matter which one, or sorry, one of the aromatic carbons. And that actually is what breaks up the aromaticity right there. Because now all of a sudden we've got too many electrons for it to be aromatic. So lots of single barbed arrows as it is a free radical mechanism, but they're all happening at the same time. Break two of the pi bonds, and you make one new pi bond. You get a lone pair here. So then methanol is just a proton source. So you donate an electron, which makes a lone pair and a radical on opposite sides from each other. Then you propagate that lone pair. And then we have a radical intermediate that's, you know, about as stable as radicals get. And if we have more sodium around, that's a really easy way to balance out those electrons again to get us back to an even number of electrons. Is you just do it again. So all things considered, this is actually a relatively simple mechanism compared to some that we've seen. It's just tricky in that it's radical based. Now, what this doesn't explain is why we wind up with our sp3 carbons directly opposite from each other, because this intermediate or even the anion seems like it could resonate with these pi bonds pretty well in a way that creates a conjugated system at the end. So I don't have a good answer for that one. We're pretty certain that this is how it happens because it's similar to the dissolving metal reaction. It's pretty well studied as well. And it makes sense up until the point where I don't know why we only get one of these. Especially when conjugated dienes are typically more stable than isolated dienes. You have to go take more organic chemistry. Go take upper division organic chemistry. I probably knew at one point why that happened, but it's been a very long time since my undergrad days.
It seems Cause at the intermediate where it's just the one radical at the bottom, right in the
Mhm.
middle. Like it almost seems like it's preferable for it to rearrange because then you turn into a conjugated. I guess it is already.
Putting the radical here or here,
I was just thinking having like the two double bonds next to it in the conjugated position, but. I guess with the radical being there, that's in its own p orbital, so it is already a conjugated system anyway.
Right.
Okay,
so it's conjugated no matter what, it has both this one and this one are gonna have two other resonance structures.
right,
But for some reason, this is the resonance structure that actually reacts. It might be something as simple as sterics. Cause if you remember that the energy benefit we get from having conjugated dienes versus isolated dienes wasn't that great. It was, 15 kilojoules per mole. It wasn't a huge leap. All right. Do one more slide. Again, needing to rearrange it so we can see it better. So if we have substituted benzenes, this might actually explain some of it. Substituted benzenes only produce certain isomers. If you have an electron donating substituent, which is going to be basically carbons that are sp3 carbons, are our biggest electron donating substituents. Your electron donating substituent only show up on attached to the pi bonds in the allylic position. We don't observe our electron donating substituents on the sp3 carbons. Which that kind of makes sense because considering the first step was you have to give an extra electron to something, the extra electron is never going to go to the carbon that has the R group on it because that's extra electron density. Why are we going to force an electron into a high electron density system? It's already hard enough that we're trying to put it into a benzene ring. But out of the benzene ring, almost any of the other carbons are preferable. And same for that resonance structure for that matter. Because that resonance structure that was either a radical or was a anion. We're not going to put an anion directly next to the R group because it's already electron donated. And as you might expect, electron withdrawing groups, we see the exact opposite. If electron donating groups only show up on the sp3 carbons, electron withdrawing groups only show up on the sp3 carbons. I think I mixed that up in the drill, so I'm going to say it again. Electron donating groups only show up on the sp2 carbons at the end. Electron withdrawing groups only show up on the sp3 carbons. Right, and again, electron withdrawing comes down to two things. Either a conjugated pi bond or a really electronegative element. So if you have an oxygen directly attached there or a chlorine or a fluorine. But the most common electron withdrawing groups are going to be conjugated pi bonds. if we ever have a situation where these conflict, electron withdrawing typically is the most important. In most circumstances, electron donating is a more subtle effect. It's not as strong as the electron withdrawing effect. So the more important aspect is that your electron withdrawing has to be on the sp3 carbon. Especially when we get into aromatic substitution. But it also applies here as well. So for instance, if we have benzene where we had methyl group and an acid group in the para position, they can't both be satisfied. The methyl group wants to be on a pi bond, but the acid group wants to be in the sp3 carbon.
So you would see that preferentially would have the sp3 on the electron withdrawal group. So
Say that again?
you would see that it's preferentially wanting the sp3 on the electron withdrawal.
Right. Usually, if they're not para, they're not opposite from each other, there's usually a way you can arrange the pi bonds so that everything's satisfied. But there are certain cases where you can't make everything satisfied. In which case, electron withdrawing takes precedence. All right, let's take our break. Come back at 5 after, and we'll do some more practice with these. And in the meantime, I'll get the slides saved and uploaded, and then I will find the. I'll give you some homework over break. Anybody wants to, if you can, mastering organic chemistry probably has an explanation for why we only see that certain isomer in the Birch reduction. So if you get the itch during your break, see if you see anything there.
Get a donut right now.
Get a donut. That's more important.
And then now the sugar rush. You want anything from the table if they're still out there?
No, I'm okay. Thank you though.
$9, so I say no. It's like 2 slices of bread.
If you can just hold out till noon and then you go to Yellow Sub. Because yeah, those, if you're gonna spend that kind of money on a sandwich, you might as well spend that kind of money on a sandwich. They're pretty good these days. There was a little dip initially when they changed hands. But they're really good again.
What did you say it was called? Yellow?
Yellow Sub,
Yellow stuff?
it's over by Sprouts by the lake.
Oh, okay.
Like behind, there's like a thrift store back there in a Brazilian jiu-jitsu place.
Yeah.
It's in that little strip mall.
Okay, yeah. I love Sprouts.
Oh yeah, their hours were really hard for a while. They were only open in the summer with decent hours. During the shoulder seasons, they shut down to only being open for like 2 hours a day. And yeah. And then I think somebody retired and somebody else bought it. One of the workers bought it from the old boss, and then they made it bigger. And
I've always liked that place.
Yeah. As long as they're open.
Yeah. That's the same thing with like Chico's. Chico's probably has like the best burger in town, but their hours are just obnoxious.
You know what bothers me about Chico's is that they only make their breakfast burrito for breakfast. And if you're in California, you can't do that.
Not going to burger place for breakfast burrito, I don't think.
No, the Chico's burritos are really good.
Are they good?
Like, even though like just the regular burritos are one of my favorite burritos.
They have the best shit in town, like their tacos, their passport tacos, they put pineapple on it, it's so fucking good.
Yeah, Chico's awesome. I love Chico's.
I guess, yeah, that burrito sounds fire too.
Yeah.
But they're never open. Drive across town just to see that they're closed.
And
Big Daddy's, but it's such a bummer there. Nowadays,
where?
Big Daddy's. It's a burger place, Safeway, it's right up there, CVS, across from CVS.
Oh, gotcha, yeah.
Yeah, it's, I mean, it used to be better when my friends were there, get a deal, and it's cheap food, but now it's like still $10 a burger. Damn. That is.
Yeah.
Yeah, $1.25 though, and fucking,
Dude, everything. It's like you go to like
guys,
Taco Bell now and you're just down like $15,000.
crazy.
On MLC right now.
Not seeing anything about it.
Then I'm not seeing why it does the like.
I'll look into it later. My print copy of the solutions manual walked off at some point. Somebody borrowed it and didn't bring it back, which is okay because I have 1568. There is a solutions manual to a lot of the problems that I assign for Klein. Yeah. There's even a digital version floating around. There's a physical version floating around somewhere now too. Somebody borrowed it and didn't bring it back. Which I'm not going to point fingers, but it's a decent chance it's either Brad or Cody that has it.
Was it the binder?
Yeah. It's in, is it? Okay.
So it's in the library and it actually has an actual barcode report that you can scan.
I think, you know what, I think Cody bought it originally, and then when he finished the OChem series, he gave it to me. And then started tutoring OChem and asked for it back. That's probably makes the most sense and just keeps it in the library.
Because it's there.
Cool. Yeah, so that is for the Klein textbook.
And if anyone ever needs it, I can always just go back there. Get it. So I know where it is. In the archives.
All right, 1568.
That's textbook, and we gave you two different textbooks that are not the right ones. I was like, these are.
Yeah, no, there's quite a few of them in the back there, but. I know where the Klein one is, so if you ever need it, just solve it.
What we were missing is that it has 3 methyl groups. It actually doesn't have as much symmetry as we thought.
Oh. For what?
That problem we were looking at the beginning.
Oh, was it that? Oh.
That
We were close. but-
it is two esters.
Yeah.
So it was 2S, yeah.
So this is why we always have to re-examine our assumptions, right? We started by saying it's probably got a whole large degree of symmetry because there's so few signals. Yeah, so
It's just a lot of. crap.
there's a methyl group, but it's highly de-shielded, so that's our singlet.
Yeah.
There's our methyl group next to a CH1. I'm not sure why that methyl group is showing up as a quartet. Unless it was this one showing up as the quartet. Cause it's next to
Then there should have been a doublet somewhere. Which I don't remember. if there was.
that, this one, yeah, then it should have been
But wasn't there a
a,
dog?
oh, never mind, sorry, I'm looking at the wrong one.
Well, yeah,
1568 is the one
That
below it.
was, yeah.
Wait a second.
okay,
This one.
okay, so we were right with this.
Yeah. And we did draw that.
Yeah.
So there's our triplet. There's our quartet. This should also be a triplet, though.
We drew that without. And that was, that's.
We thought about putting those in the middle.
Well, no, we knew we had the CH3, CH2 going on.
So we made the mistake of putting too much emphasis on the splitting, and we know that splitting is inconsistent sometimes.
Right there.
You know.
Yeah, because we did actually, we drew this at one point,
You did.
And we said, well, but the splitting doesn't work.
Yeah.
Because we had a singlet in there. But those must show up as a maybe because, you know what it is, it's because they're the same proton, they're identical protons. They don't cause splitting with each other. So that's our
Oh, so it shows
singlet.
up as one.
It shows up as one because those hydrogens are identical to those hydrogens.
That one was kind of a tricky.
Oh, yeah, thanks, forgot about that. Good to know.
Yeah. I had thought about that at some point, like, but on the spot, I couldn't come up with it quickly. So
Now, this one,
there's something about them being identical that messes with splitting. I couldn't come up with it on the spot.
Under pressure.
what,
That's what.
how do we know that the esters are in that orientation versus like the carbonyl being towards the outside?
Mostly because of the splitting, we could, yeah, the other option. So one of the things, and this is by no means definitive. But in general, esters tends to be more stable. When the oxygen is pointed towards the smaller part of the molecule. And that's just, those are more common molecules, so part of it is like. Is that, but if we actually got out the chart and we looked at a CH2 group directly attached to an oxygen. Versus, and then this one, they didn't show up with the same shielding, right? This one was de-shielded, but not as much as that one. If I'm remembering how it showed
Yeah,
up.
it was. Yeah.
So directly attached to the oxygen is gonna be more de-shielded.
Yeah.
And it's, because the other example would look like. That one, our singlet would have been more de-shielded, and our doublet would have been more shielded.
So it would have been just switched around.
They basically, you probably almost 1-to-1 swap where those two groups are.
Comment about that.
Sometimes all that you need is the solutions manual.
Yeah. So when symmetry, we need to worry about identical carbon, not custom, right?
Yes.
Yeah.
That's the, there we go.
Yeah. Well, and this is the sort of thing where you can obviously trip yourself up by asking these questions if it's not the field that you live in. That would have been a really easy one for somebody who, a third-year student who's in the thick of their organic chemistry classes, would have looked at that like, oh yeah, symmetry, no splitting, would have been right on, first thing they thought about. But because it's not the field that I live in right now, I missed that. All right. So let's do some practice with these first reductions. So A, we got isopropyl group. Is that donating or withdrawing? Donating. So it's got to go on the SP2 or SP3? SP2. And when there's only one group, that's easy enough to draw, right? You don't even have to change the orientation. You're gonna do that. Then for B, they're both donating. And they're para. We should be able to satisfy both of them with that, right?
Yes.
Can we still satisfy everything if they're meta rather than?
Yeah.
Yeah,
Yeah.
we can't put
Oh,
it
yeah.
down here,
Yeah.
but if we put it there. And what if they're ortho? If they're ortho,
Yes. Yes, because they're on.
you look at the other carbon, go the other direction, or go the other way.
Oh, right on, there it is.
Right, or if we wanted to keep the substituents in the same spot. You do that. That just means we just change where we draw the pi bonds, but as long as our pi bonds are opposite from each other. That's fair game. How about E? That's an electron withdrawing group. Which means it goes on the sp3 carbon. And it's a little counterintuitive when you think about it from the thermodynamic point of view, because we don't get any resonance this way. But so the fact that we're not getting any resonance in our final product, as well as thinking about those intermediates, tells us it must be a kinetic issue, because we know that the final product would be more stable if we had more resonance. And the fact that that's the opposite of what we observe tells us it's a kinetic versus thermodynamic issue. If you think back to that lab. Thermodynamically, it favors more resonance, but kinetically, the intermediate must be more stable, or the transition state must be more stable this way. Alright, so then last but not least, we have a donating and a withdrawing group.
This one works out nicely.
This one works out nicely. So if we have our. And again, as long as you don't have donating and withdrawing in para position, you can almost always find a way to make everything satisfied. There's, when you start getting tri-substituted, then it gets a little bit trickier. Like, for instance, if we had that, we can't satisfy all three of them now. But the nice thing is, well, it's symmetric, you get the same product either way, but what we'll get is we'll just get a mixture of products. Or 2 out of the previous sets.
I was about to ask what would be preferred.
If they're all donating, then they're all relatively the same strength in terms of donating. Because donating is a kind of a weak effect. So in that case, you're just gonna get a mixture of 2 out of the 3 are happy. If it's an electron withdrawing, we'll actually learn that there's a scale of how strongly withdrawing the groups are. And what'll wind up as long as the most withdrawing group is satisfied is the most important. And in this case, we've got a donating and a withdrawing. In their meta relative to each other, so we can actually put it in either position, right? It's identical. This is a good one to spend some time on because it does make us think in terms of ortho, meta, para, and think about different ways of rearranging things, spinning things around. So since it's been a while since we did that. All right. Y'all are just, you're keeping up. And maybe I'm just moving faster, but we keep finishing my slide decks before we're, this would have been a full.
Wait, are we?
We're not quite done yet. There's one.
I was about to say.
We're close. We're only 4 slides away. So. We'll section 1 on spectroscopy of aromatics. So 1. We're looking at IR spectroscopy. There's a couple of really common characteristics that we see. So these ones are a little bit harder to make up because these peaks are down right at the edge of the fingerprint region, and they're not reliable. Sometimes they're buried in the other vibrations that we can't really do much with. And this one can wind up getting overshadowed by a carbonyl. It's close to where we find carbonyls a little bit lower. But again, it's getting into that region where it's hard to tell if that's fingerprint region or not. But what we do see, those have a nice amount of symmetry to them, right? And they're in an area where almost nothing else shows up. So they're weak peaks. But the fact that you should have more than 2 really, and they should all be equally distant from each other, almost looking like peak splitting in an NMR. How they're all the same distance from each other. And it's because those carbons are really, even if you have substitutions on it, those carbons are really close to the same energy, those bonds. Right? Because of all that resonance that's happening. And so that's why they're called overtones. That's a musical sounding term, right? Because basically they show up as a reflection of all of that symmetry that you have. They're stretching in certain ways that only happen if it's aromatic and if you have a high degree of symmetry among those carbons. And so those should show up even in substituted benzenes. You should see some weak peaks equidistant from each other in that range. If you also have an NMR though, the NMR is a lot easier to tell if you got something aromatic, right? It's really smoking gun. It's like alcohol with an ion, right? But one of the things that you can look at is what the different bonds are, because if it's just a sigma bond or even a pi bond directly stretching,
those are really easy to understand. Some of these other ones, these combination bands and overtones. They're actually a combination of atoms moving at the same time. It's not just two atoms stretching apart from each other. It's more like. I always go default back to talking about guitar because that's the instrument that I play. But if you have you strike a guitar string in the right note, string next to it will start vibrating as well because they're vibrating the same frequency. And so it's more than just one bond stretching, creating these. It's several bonds stretching in concert. It could be one of these bonds could be all three of these moving to the right and all three of these moving to the left. Maybe turn it back into being benzene, at least. Like that's gonna have its own frequency, right? It's slightly different than just this carbon moving away from that carbon. And then you could also do these two move that way, and these two move that way, and these two move that way. That's gonna be it's gonna be close to the same energy because it's still a carbon-carbon bond stretching at its root, but it's in a different direction. And so it's a slightly different energy. But that's why we get this symmetrical aspect here, why they're all the same distance apart, and why they're so weak compared to a straight carbon-carbon pi-bond stretching. Is because there are these overtones that are sort of embedded within the other stretching that can happen. Right, we only really see that when we have all of these sp2 carbons in a ring structure. Because you need to have that ring structure for either of those larger two vibrations to happen. We don't have that ring structure, we don't have anything holding it in place, and then we just actually have rotation happening. And it turns out that you have, and I always, you go back to the definition of the number of possible vibrations you have is going to be, it's either 2n minus, it's not a symmetrical molecule, it's 2n minus 6 different distinct vibrations where n is the number of nuclei. So you can see where if we have 15 atoms, we wind up with 30 minus 6, we wind up with 15 distinct vibrations that can happen. And all of those vibrations are going to show up in here. And that's not taking into account that different molecules can interact with other molecules. That's just within the same molecule. Right, and so as you get bigger and bigger molecules, obviously that's going to be trickier and trickier. You're going to have more and more crowded fingerprint regions, especially because a lot of these weaker vibrations happen down in here. And when you see things like CH bending, that's something that looks like, so CH stretching is just out and back like a spring, right? But if you picture flicking this hydrogen, holding the carbon in place and flicking this hydrogen sideways like one of those spring door stops, it's going to go back and forth like this, right?
And each atom, there's a little cat sitting there like boing.
Right, exactly. And that little cat is called entropy. But it takes a different amount of force. Picture actually taking one of those spring door stops and pulling it out. That takes a lot more force than flicking it sideways, right? So the stretches happen all the way up here, but the bending happens down here. And there's a lot of other bends that can happen that give you signals in the IR that are all right on top of each other.
So that's why that like lower wave number areas like just
Messy.
messy.
Yeah. If we had good enough computers, we would actually be able to simulate this. We can simulate IR spectra for molecules, but they don't get all of these right in terms of their, because there's so many variables. With a better computer, as computational methods and computers get stronger and stronger,
we get better and better at just simply making this up ourselves. And then it's more of just matching it in a database as opposed to actually interpreting it.
I think that might be a good job for a quantum computer, like so many states that are.
Right, because when you have all those mixed variables together, that lends itself to some of the ways, and I'm not a computer scientist, so. Knowing there's something fundamentally different about the way you program things in quantum computers. And I don't know enough to speak about it too much depth.
Dude, folks, it's
It's not 0 or 1,
it's not 0 or 1, it has a 0, 1, or 2, or 0 and 1, or.
Right.
1 and 2.
And then
or
it gets
0 and
trickier
2.
that because when you measure something, it actually collapses the wave function and now no, it's no longer a superposition of both. And I don't know how you program that. Smarter people than I.
Yeah, that's.
Yeah.
one of my
Are
best
working
friends,
on that.
he ended up, he's working for Honeywell or quantum error correction
Mhm.
department, how to figure out how to overcome that problem of like error being introduced into the.
Right, every time you recall your data
Yeah,
changes.
exactly. So there's clever ways to get around that, but I don't understand it.
Yeah. All right, and then as we mentioned before, as we've seen in lots of cases. Proton and NMR are really easy to spot those hermits, even carbon and NMR, and they still show up in a really distinct area. Splitting, we don't see a whole lot of useful splitting, except in 2 cases. Both of those. There are more in-depth graphics like this, but the easiest ones to understand are when we have a di-substituted benzene in their para. If they're para relative to each other, either all of your, if X and X are identical to each other, if your 2 constituents are the same, then all of your protons are identical to each other, and you only get a singlet with an integration of 4. I guess, in theory, if you had a tri-substituted benzene, where all of these substituents were the same, and they were meta, that would also give you a singlet, except with an integration of 3 in that case, right? So if you have a high degree of symmetry in your substitution, then sometimes you can see that if they're not identical and they're para, then really you don't have one mess here, you have these 2 protons and these 2 protons. And each of those groups is going to be have one nearest neighbor. So if you're di-substituted benzene and your substituents are para and unique from each other, you should see 2 doublets, each with an integration of 2. If we had a tri-substituted benzene, where everything was unique, and it really doesn't even matter, right, with the third one. If it's tri-substituted and they're all unique, then every single one of these hydrogens is unique. And you might be able to see 3 triplets, or sorry, 3 singlets. But they also might be on top of each other. If X and Y are an isopropyl in an ethyl group, they're really close to the same splitting, right? And that would mean that this one and this one and this one all might be really close to each other, sitting on top of each other.
Could it appear as doublet if they're so close?
No, they might overlap. It might look like a doublet, but they should have different intensities. It shouldn't be this nice symmetrical doublet if it's 2 different signals. And even if we did something like this, all 3 of these are still unique now.
Right, so tri-substituted, you probably will be able to see 3 distinct signals. And this one should look like a doublet, and a triplet, but all in close to the same area, and that's when you get a multiplet. Where you're just like,
The triplets, a doublet of doublets, and then.
Right.
You know what, different doublets.
and again, if you live in this world, if this is what you're studying specifically, or if you're a grad student specifically in organic chemistry specializing in NMR, you probably are looking at that. But especially if you're taking your own NMR and then you got other characters like some impurity in there throwing stuff off. Like it gets hard to actually take something like this and turn it into a doublet, a triplet, and a doublet on top of each other. You could, in theory, Fourier transform this and separate it out into 3 separate signals if you know it's 3 separate signals.
Right.
But the data gets messy when you're actually taking your own data. And it's usually enough to just know this, and then you can work out the substitution using other means. And it really doesn't matter if it's integral is 5. The integral is 5, then what do we know?
There's just.
Which means it's a mono-substituted benzene.
Yeah.
And it doesn't matter where you put it because they're all the positions are identical to each other. And honestly, probably with that tri-substituted, if you can't separate it out.
Integration does not go on.
And integration's gonna be really tricky, you'll get the whole mess as integration of 3. But if you can't separate it out, the splitting to figure out where the substitution is. Carbon NMR. Will probably be a way that you can do it because you'll be able to look at your carbon NMR. And actually have it have distinct signals, they still all might be really close to each other. But that actually might be enough for you to actually say X is here, Y is there, Z is there. Carl and I were just talking the other day, we get so used to these magnetic erasers now.
Oh.
That there's one eraser in the chem lab that doesn't have a magnet in it still, and I do that and just throw it on the ground. All right, so here's our common substitution patterns of carbon NMR. So if the proton NMR is too convoluted to break it apart. Substitution patterns in carbon NMR might be more helpful. So in particular, if you know it's di-substituted because you integrated the proton NMR, but you don't know if it's para or meta or if they're the same substituent, then para should only give you 2 signals because there's only 2 unique carbons in the benzene ring. If they're ortho relative to each other, you should get 3 signals. And if they're meta and the same, we should get 4 signals. So knowing that you have 2 of the same substituent, we can actually use that pretty easily to figure out what the substitution is with the carbon NMR, because it gives us that better resolution and we don't wind up with the splitting overlapping with each other. If X and Y are different from each other, then if they're ortho, you get 6 signals, and if they're meta, you get 6 signals. And if they're para, you get 4 signals. Differentiating between these is gonna rely a little bit more on looking at de-shielding and the exact order of the signals. But just the sheer number of signals allows us to narrow it down a lot, right? If we have the carbon NMR. And if it's mono-substituted, again, that's really easy to see here. Integration of 5 on the proton NMR and 4 unique signals in the aromatic region in the carbon NMR. Boom, done. Mono-substituted benzene. Which seems like you shouldn't need both of those. You should only need the proton NMR, but again, the integration sometimes when you're actually taking your own data is not as clean as when we're giving you the data. So sometimes you want to support it with additional information. What would the carbon NMR look like for tri-substituted? Well, if they're all the same. That should also give us, 4 signals, right? Or 2 signals.
Or
I think 6,
6.
because this carbon is adjacent to an X and meta to an X. This carbon is adjacent to 2 X's and meta to 1 X. So those are gonna show up differently. Those 2 are gonna be different from each other. That's different than that one. And that one. So I think you get 6. So there's a lot of ways you can get 6 signals when you start having tri-substituted. All right, so one more of these with all that information now. Yeah, let me slide that up. All right, and the formula, can't really see it, is C9H10O. It's aromatic, not really that. Because we've just been talking about aromatics.
Number of carbons, hydrogens.
Number of carbons, hydrogens, proton NMR. Those characteristics, again, they're weak, but those overtones are right there.
And the 1450, 1500, 1600 peaks are all.
Got it. Pretty clean. The rest of this doesn't have a whole lot in the fingerprint region. So if you're lucky that you can use some stuff in the fingerprint region to support what we already thought. We wouldn't want to look at this and immediately think aromatic. In the absence of more information, we might think it hints at being aromatic. But we wouldn't want to put it conclusively until we see this.
And the Sp2CH stretch in there.
We definitely have Sp2CH stretch. Several of them. Again, this is not reliable. You can't reliably count the number of peaks to say the number of unique carbon hydrogens. Because sometimes you get weird overtones and things like that happening too. We do know there's an alcohol. So we're probably looking at a phenol. But at the very least, we know we've got this. So there's 6 carbons. We know from the integration that's a monosubstituted benzene. In our carbon NMR, this is actually fairly common that your signals might be pretty small relative to the noise because of the way we had to tune the detector. The response rate is just such that you don't. It's a little bit like AM versus FM radio. When you switch the frequency by that large, when we're looking at carbons versus protons, there's a lot more interference and the signals themselves get weaker because we have fewer carbons that are actually going to show up. So you do see things where your signals are just barely more than the noise sometimes. So in this case, that we were kind enough to label it for you. About 1, 2, 3, 4, 5, 6, 7.
Makes sense, because We'll have 40 carbons.
We'll have 4 unique carbons in the aromatic region. Probably those. And then, so we're gonna have 3 more carbons, which again, makes sense, 6 of our 9 are benzene ring. So 3 more that are all unique from each other to each other. One of which has an OH attached to it, right, because we know it's not a phenol. Because our benzene is monosubstituted.
You know, we use like the entire time.
Don't have anything down in the. Unless I just
Overlapped. I think. Yeah, no, that's the whole thing. I want to make sure that I didn't.
lose a methyl over there. We don't really have anything showing up in the methyl region. Or with the right integration for it to be a pure methyl. So one of these could have an OH on it though, that could be de-shielding a methyl to put it in this region. And then that would make sense for the splitting if we had a CH2. CH2, OH. That should give us 2 triplets. The methyl being de-shielded down into the same region. It's hard to say which of these is which of those 2 carbons. But that would make sense with the integration. With the splitting.
Who's missing a carbon in the group?
We're just missing a carbon somewhere. Anybody have your figure? Is this 201? Is this the alcohol?
I think so, yeah.
I think OH carbons directly attached to an OH group show up down here. These 2 are pretty close to each other.
Carbon attached to the alcohol should be like 50 to 70.
So maybe this one.
Because I'm thinking the one that's above at the 201, it's just saying aldehyde and ketone,
Okay,
which is,
so let's look at our number of hydrogens to see if that makes sense.
yeah,
Could this be it can't be a carboxylic acid.
no. But it looks like we have an alcohol.
It looks like we have an alcohol. That's usually a smoking gun.
Yeah, like that's pretty. There's no nitrogen in there. Not named.
Does anything else show up in that 200 region?
I'm looking at this compound interest one.
Yeah.
No, so it's just those 2.
Aldehydes, ketones, even carboxylic acids are a little bit lower.
Yeah, like under 180.
Well, and what shows up in the proton NMR over here?
Over 10. That also is aldehyde or carboxylic acid.
Right? And this peak right here. It's pretty indicative of an aldehyde as well.
And we don't have the carbonyl.
And we do have the carbonyl peak as well. So maybe this is a little impurity. Maybe we have a little bit of our alcohol mixed with our aldehyde.
Yeah.
Because then. If that's our R group, everything makes sense except for. The alcohol looking peak.
Yeah.
This is why experimental data is both fun and infuriating, right? Because. Yeah, you have to examine your assumptions the whole way through, even something that's one of the first things we learned about IR.
Yeah.
Very first thing I taught you to look for was that, right?
It was one of the first things we went for.
Right, but it makes sense with everything else. That means aldehyde, that means aldehyde. And our other signals make sense.
I guess here though, splitting, it's kind of weird because the one should be a triplet, right? And then the CH2 that's in the middle, that should be a doublet of triplets.
So,
Should be,
but again, we know splitting is one of our least reliable
Right.
aspects of the NMR.
right.
Is that a doublet of triplets?
Could be.
But then, so in that case, we would expect it to still have one more signal showing up somewhere, and this whole thing would have an integration of two. So that's probably both signals. It's probably just that the splitting, maybe, you know, because we have seen issues where like alcohol hydrogens don't show up in the splitting.
Oh, yeah, because it's deep.
Because it's because it's de-shielded enough that it's not interacting the same way the others do, so. Given that this aldehyde hydrogen is so de-shielded, showing up all the way over here. It's not unreasonable to say, well, that one's not gonna affect the splitting of this because they're so different in terms of how shielded they are. Just like we wind up with the alcohols, sometimes the alcohols don't even show up in the proton anymore.
Right.
Period, let alone show up as affecting other splitting. So remember that. And this might be just de-shielded enough for that to happen.
Gotcha. Okay.
And since we have 5 more minutes. So we're pretty sure that this is gonna be 3-phenyl propanaldehyde. Would make the most sense, right? So let's check our answer. This was 1755. And actually, I'm gonna drag that back over here. So I can get to the right chapter. 55 is probably towards the end. I've lost my cursor. There we go. Yep. And they broke it down pretty much the same way we did. We knew we had 2 CH2s. We knew we had the benzene ring, and we figured out pretty quickly we had the aldehyde in there too, even though our first thought was alcohol. And it probably mentions in here in the explanation somewhere that the alcohol signal or the alcohol signal is.
Oh, it's on the bottom of the page.
There's a signal.
Yeah, exactly.
I'm curious.
Curiously, they didn't come up with a question.
Although a bit weaker than normal.
Yeah, it did look like it was a bit weak.
Yeah, it wasn't.
So this is perhaps due to the enol form, because these things do go through rearrangements, right?
Polymerization.
So if you had the aldehyde go through tautomerization, we would get that primary alcohol like we thought
But the double bond.
with the double bond here.
Okay.
And that's not gonna show up in the NMR. Because it's usually like a 15 to 85 ratio. Where 85% of it is present as the aldehyde,
But the IR can
and the
show up.
IR will show up just a little bit. Because the IR less about the interactions of the protons with each other and just more like everything that's present can give you a signal. That would make a good explanation, or just some sort of impurity. When you're dealing with real data, that's what you get sometimes. They packaged it in the same bottle with some phenol or something on accident.
And again, those NMR spectra too are cleaned up a fair bit. There's less noise than we would normally expect to see in a real.
It's very like perfectly level. Usually there's at least a little bit of noise. Signals are way bigger than the noise is for proton anymore, but there is still some noise. So if that was the case, we might see some other weaker signals that would indicate we had the raw data rather than the processed cleaned up version. All right, that's all for today. And it did wind up being right around the right amount of time. Quiz this weekend and that review. Any questions you want to go over from the review? Let me know. But in the quiz this weekend, just aromatic versus anti-aromatic stuff and just a couple of those basic Birch reactions and oxidations. Okay. And it'll go live in a couple hours. So go eat some lunch and then come back to it.